My name is Wolfram Mauser. I'm coordinating the Virtual Water Values project, and I have brought the team with me to have this session, and we will show you a regional example. ViWa is a global regional local project. So we have a global part of the project, but we will not address this here. We will show you a regional example of our work, and we call it the Water, Food, Energy, Ecology Nexus. But who is we? First of all, I introduce the partners in ViWa. First of all, this is Department of Geography here. And Mr. Heinzeller, who's also in the audience, he will take your questions, if you have questions, and organize the questions and answer session during this side event. There is the Institute of the World Economy that is participating in global questions. My colleague Gernot Klepper. There's the Helmholtz Center for Environmental Research in Leipzig, and Estanis is here from the research center to give us his presentation. The Institute for Environmental Planning at the University of Hanover. Anna is here, who will show us her results. There is the Helmholtz Center in Geesthacht, the Climate Service Center. They have done extensive global simulations of climate for us. And there is the Leibniz Supercomputing Center of the Bavarian Academy of Sciences in Munich. Stefan Hachinger is here, also in the audience. And there is, last but not least, Vista Geoscience Remote Sensing in Munich. They have done the extensive analysis of the satellite images that we use. We have a homepage if you want to know more, even more than we can show you today. There is the homepage here. Wait a minute, I have to get me a cursor here. Switch it on. There is the homepage here that you can use to get even more information. So now we have chosen the Danube Basin for the Water, Food, Energy, Ecology Nexus example. Danube is the most international, very diverse, large river basin, 19 countries, 800,000 square kilometers. And a few years ago, we were not even thinking about simulating processes across a large watershed than this. So this is not as a large watershed. This is a huge watershed in terms of hydrology. The Danube Basin is moist upstream. We have precipitation of more than 1,000 millimeters per year, and much drier downstream, down to 450 millimeters per year. So you see there is already an upstream-downstream conflict in terms of access to rainfall. The change of system in the post-Soviet era, it's important to understand the Danube Basin, because the Danube Basin is composed of Central European and Eastern European countries. It resulted in a total collapse of the agricultural infrastructure in large parts of the basin, and a reprivatization of agricultural land, for example, in Romania. So the EU and the International Commission for the Protection of the Danube River Basin, the ICPDR, situated in Vienna, they are responsible for basin-wide governance, and they are the ones who try to get over the Danube countries' national interests under the EU. So there are still strong national interests under the EU. There are some countries who are not yet members of the EU, also like Serbia. So they all have their own interests, and they all have conflicts related to water. All the basin countries depend on the Danube water as an economic resource. The water competition is between agriculture, power production, industry, transport, and household. So almost everybody is competing for water, specifically in the downstream regions of the Danube, and not so much in the upstream regions, where we have this huge water tower of the Alps that supplies large parts of the watershed with water. Again, this change of the system in the post-Soviet era, it provided almost 2 golden decades for the ecology in the downstream Danube countries, because of all these systems collapsing and the decreasing influence of industry and agriculture on the environment. So the Danube, in large parts, this is downstream picture of downstream Danube. Here is a wonderful river which is almost naturally flowing. So we have 2,860 Natura 2000 sites in the Danube, and we have the Danube Delta as one of the world's largest wetlands, and as UNESCO World Heritage Site. So there is a lot to protect in the Danube. And so the conflicts are not only within the economic sectors, but it's also a very strong conflict with the ecological, the interests of nature. The EU Danube strategy is pushing hard to reintroduce the sturgeon in the Danube. And I think they will be successful. So the water quality has increased. So sturgeon will maybe become a normality again in the Danube. So wait a minute, white screen. What's happening? Do you see my screen?
No, we didn't see it anymore. I think you. Yeah, now.
Okay.
I think you put the W.
I put the W?
Yes,
okay.
But now everything is fine again.
And now everything's fine again. Okay, wait a minute. So I'm a bit confused at the moment with my slides, but this is the slide that. So the EU membership in 2004 and of Hungary in 2007 for Romania, they were instrumental for bringing the countries together. But the middle and lower Danube still have low intensity agricultural use. The yields are often limited by water stress in the summer. So large yield increases are expected through irrigation, but presently only 1.5% of the cropland is already irrigated. So there's huge potentials for irrigation. And the Danube countries plan to expand irrigation with about 3 billion euros of investment per year over the next years. So there is a huge investment in infrastructure planned specifically in the downstream regions to intensify agriculture through irrigation. And this made us very interested in the Danube case. And this makes the Danube case a very interesting case altogether, because the Danube is approaching or expecting major changes in the use of its water. So our major question is, our major research question in the water, food, energy, ecology nexus, which I show you here. You have the rainfall water, and the rainfall water is converted into, into food, and and the water is leaving the watershed through water consumption. But then you have food for the global food markets. But it can also be converted into energy, into hydropower, for example, where you have hydropower for the supranational European markets. You have an impact on the ecosystems. So you have water conflicts that you create. And these water conflicts are in the center of our water, food, energy, ecology nexus at the Danube Basin. And the major question is for us, which conflicts arise between water, food, energy, and ecosystems from fully realizing irrigation potentials in the Danube Basin, which are now on their way. So, and our case study that we will present today as an example is the expansion of irrigation in the whole Danube Basin. Maize is the most likely candidate. Maize is growing in the summer. Maize is experiencing major water stress in the Danube Basin. So investigating economic and ecological consequences are at the center of our example. This example has become quite prominent in the Danube countries because the ICPDR, the International Commission for the Protection of the Danube River, uses our simulations together with us to inform the national ministries for environment and agriculture in the form of workshops on the consequences that can be expected for the environment if irrigation is cranked up or will be cranked up. So this is what you can expect from the presentations that will follow my presentation. My presentation is now only an input, but to give you an overview, it will be followed by the presentations of how do we model this water, food, energy issue in terms of first of all, hydrology, but then also agriculture. Both sides have to be in the boat, and groundwater. Then yield and water use efficiency in Romania as a case study, then remote sensing for regional nexus research, which is scaling up the Romanian experience to the whole basin and to all of Europe. Then irrigation impacts. What are the impacts of irrigation on the water, food, energy nexus? And at last, the synthesis, the ecological consequences and the synthesis that comes after that. So after each of these presentations, there will be a short question and answer opportunity for you, and we will have a whole roundtable question and answer session after the synthesis where you can pose all your questions. Now, with this, I will finish and I hand over to Elisabeth for the next presentation. Thank you very much.
Yeah, thank you very much for this introduction, and also from my side, good morning to everybody. My name is Elisabeth Probst from the LMU of Munich, and it's my pleasure to present you some of the research outcomes in the Danube Basin. So the topic now is water balance and discharge. The Danube Basin is the pilot catchment, as you have already heard, for our Nexus assessment in ViWa, and I will show you now some general developments in terms of model setup, water balance and discharge, which forms the basis for all following work in the Danube. So let's start just with some more few hydrological characteristics maybe. Yeah, as you have heard, the Danube is Europe's second largest river basin with a catchment area of about 800,000 square kilometers. And it is also Europe's second longest river with almost 3,000 kilometers from its source in the Black Forest to its outlet in the Black Sea. And here at the outlet, the mean runoff amounts to about 6,500 cubic meters per second. And the Danube comprises also subbasins of very different topographic characteristics. So there are mountain watersheds as well as lowland watersheds. And this is why the Danube features complex hydrological characteristics which are challenging for hydrological modeling. So the major question we like to answer is, can we simulate the complex interlinked hydrological and biophysical processes in the Danube by the help of a mechanistic model? So the core of our activities in the Danube is modeling with its hydrological modeling with the model BROMID. So a few words on the setup of our framework. BROMID is an hydro-agro-ecological model. It interlinks hydrological modeling and biophysically based crop growth modeling. It also operates on a spatially explicit scale at a custom resolution. We chose here 1 square kilometer as resolution, and simulates on hourly time steps. For the Danube, in this case, BROMID is driven by the global reanalysis dataset ERA5, which is dynamically downscaled to 1 square kilometer and also bias corrected by precipitation climatologies. BROMID also requires gridded input data on topography, soil, land use, and also hydrology, for which we used freely available global data sets. And plus also a set of parameterizations are needed to describe the physical processes of vegetation, soil, hydrology, and agricultural management. Now, the outputs of the simulations is gridded data on, for example, crop leaf area index, phenology, yield, as well as evapotranspiration, water use efficiency, and also discharge. The first goal now is to assess the water balance in the Danube. And for this, we divided the Danube Basin into major subbasins, which feature comparable topographic characteristics and for which discharge observations are available in a more or less reasonable time span. That is, don't have a cursor maybe, but that will work out well. Okay, that is the upper Danube, the middle Danube, and also the basins of Drava, Sava, Mureș, Discharge, Siret, and Prut, as well as the lower Danube with the outlet gorges in Reni and Seatal Ismail, which are not too far away from each other. So you can see in the map from the colors which subbasin belong to which color. And we got discharge observations now from the GRDC, which is the Global Runoff Data Center, and the ICPDR, which is the International Commission for the Protection of the Danube River. And these observations are available for very different time periods, as you can see in this below in this timeline. We use this data now for the long-term validation for discharge and water balance. So absolutely essential now for the discharge modeling is the bias correction of Era 5 precipitation, especially in complex terrains. And for this adjustment, we use a long-term climatology. A well-known data set is Workland 2, which we also use, but we learned in the Danube that the complex alpine rainfall patterns, especially, are not fully covered by Workland. So we incorporated also regional climatologies, which are much more accurate in alpine regions, and these are the global climatology for the Upper Danube, the prism climatology for the Alps and Dinaric mountains outside the Upper Danube, and finally Workland 2, the Workland 2 climatology for the remaining middle and lower Danube. So here in the maps below, you see the annual rainfall coming now from station data on the left, and the annual rainfall coming from Era 5 data, bias corrected by this mosaic of Glover, Prism, and Workland here on the right. Ah, here's the cursor. Do you see my cursor? No, okay. Yeah, and for example, this dense rainfall band in the Alpine foreland, it is here indicated by a circle, and also the dry valleys in the Inn and the Danube Basin is now very well captured by this mosaic bias corrected rainfall, which was not the case with Workland bias correction alone. So we have to incorporate regional climatologies here. So yeah, and the performance of this mosaic bias correction dataset, this also proves to be capable to model discharge and water balance when we look at a direct comparison of the different climatologies when used for a bias correction and afterwards for the discharge modeling. So you see here two indicators, which is NSE, short for Nash Substrate Index, and the KGE, short for Klein-Gupta Index. And they are two efficiency measures used in hydrological modeling, and they indicate how well the model predicts the observed discharge. And they range from 0 or negative values to a maximum of 1, which means a perfect fit in every case. So, and when we see that when we drive the discharge modeling with Era 5, bias corrected by different climatologies, we see that the best results is achieved for this latter mosaic correction dataset, while the others always have 1 or 2 subbasins with a very poor model efficiency. And poor model efficiency is indicated here in red, while a good model efficiency is indicated in blue. So this latter configuration with Era 5, bias corrected with a mosaic of Glover, Prism, and Workland, is for the use for all simulations because of its best performance. So a second important input I like to highlight for the hydrological modeling is a realistic map of the land use in the Danube, because the water fluxes are, of course, very specific for every land cover type and also for every crop. So for this, we firstly created a mosaic of Corine land cover and ESA CCI land cover. And as they hold no information on crop distribution, which is crucial for yield and discharge modeling, we carried out now a statistical distribution of crops over the agricultural area based on Eurostat cultivation statistics within the NUTS 2 administrative regions, so that the distribution of the crops statistically exactly match the Eurostat cultivation statistics within these administrative regions. So, and having this land use map ready for modeling, we must also now define a realistic management for the agricultural crops. So we take crop-specific seeding dates and growing seasons from freely available data and adjust the fertilization levels to national crop yield statistics. And as an example here, this results in an average simulated yield of 6.9 tons per hectare for the, in average for the time period 2015 until 2018, which is very close to the Eurostat yield of 6.8 tons per hectare. So now incorporating the biophysical modeling with hydrological modeling, now we investigate the water balance. And the water balance is calculated as precipitation minus evapotranspiration minus discharge, minus the observed discharge. And I stress here that we undertook no calibration on the hydrological modeling at all, but simulate with a mechanistic approach with a closed water energy and carbon balance. So with all our adjustments in terms of bias correction, land use distribution, and crop management, which was important for this for the closure of the water energy and carbon balance, we get a quite even long-term water balance over the whole basin and all sub-basins. Some sub-basins feature slight over or underestimations in water balance, but at the outlet gorge of Siat al-Ismail, water balance is 0, which is a perfectly balanced amount. So here you see now the relation between the simulated discharge and the observations. On the left for annual runoff and on the right for monthly runoff. And all the data points include the discharge at the Danube outlet as well as all subbasins for the time period 1980 until 2018. And we see that in both cases, annual and monthly aggregation, there is a very strong correlation of the simulations to the observations. In both cases, we get a trend line with its, which is very close to the one-to-one line, and the R² amounts to 0.99 for the annual values and to 0.95 for the monthly values. So now let's also have a look at the monthly hydrographs and the efficiency measures at two example gorges. Achleiten on the left, which is the gorge of the Upper Danube, and Siat al-Ismail on the right, which is the outlet gorge. And we see that in both cases, the dynamics of the modeled hydrograph matches very well the dynamics of the observed discharge. We get mesh subcliff and Tringupta indices equal or higher than 0.7 in both, for example, in Achleiten and Siat al-Ismail, and also throughout the whole basin with all sub-basins, the efficiencies almost never drop below 0.5. And also the daily hydrographs gives us very good results with well-captured dynamics. The daily efficiency measures are only slightly lower and are roughly in the same range as the monthly values, not only in Achleiten and Siat al-Ismail, but also in the whole basin. So overall, this is a very satisfying result, given that no calibration is undertaken, and also given the fact that we use a global reanalysis product like error 5 and no measured precipitation station data. So to conclude, we carried out integrated modeling of the Danube water balance by the hydro-agro-ecological model PROMET. One part here is the biophysically based crop growth modeling, which gives us actual evapotranspiration and actual yield. And the second part is the physically based hydrological modeling, which gives us discharge. And this configuration ensures that we simulate with a closed water energy and carbon balance, where the water balance and yields are very close to the measurements, and also the efficiency values for runoff dynamics are very good, to very good. And as I have said, the model has not been calibrated, so one can easily transfer the approaches to other watersheds. And we also prove that we can use global reanalysis data like ERA5 as a meteor driver for hydrological simulations, which is a very solid basis for medium to large scale watersheds. And we learned that WorldClim2 data is supportive for bias correcting ERA5 data, even though it is rather inaccurate in alpine regions, so that more local data is necessary. So this simulation scheme without calibration, but with a closed water energy and carbon balance, makes it now possible to study the complex interactions between agriculture and hydrology. So this is the basis now for our regional water, food, energy ecosystem Nexus assessment. So for now, I thank you for listening, and either you have questions now, or I can now hand over to Estanis Pujaris from the UFZ on the groundwater modeling in the Danube. Yeah, okay.
So, thank you. Are you hearing me? Okay. Can you hear me?
Yes. Yes.
Okay. Okay. Sorry. So, my name is Danube Basin. I'm a member of the UFZ team that has worked in the ViWa project together with Dr. Sabine Attinger, and we have worked on groundwater-related issues. Specifically, our work has consisted in the development of groundwater numerical models at that scales to predict the groundwater behavior and different scenarios. But why we need this model? So, well, the main reason is that, as you can see on the right, it is expected that the stress of the water resources will increase a lot during the next years due to the climate change, but also because of the growing population. And in this context, we need numerical models to predict the evolution of these water resources, and also to design water management strategies. And these models must be at regional scale because the events affecting these water resources have a global nature. So up to date, there are models at that scales, but they are mainly hydrological. That means that the objective is to simulate surface water processes. For example, with these models, we can predict the river flow evolution. So on the right, you can see one example of these models. These are the results of a hydrological model developed with the code MHM that allow us to predict the river flow evolution at the European scale. But hydrological models fail to simulate the groundwater because they simplify the underground medium and they model the groundwater using a system of buckets, which is not realistic. So in the figure in the left, you can see that most available fresh water is groundwater. Therefore, we also need these groundwater models. They are very important to predict the evolution of water resources, but also to couple them with hydrological models and increase and improve the predictions. But the development of regional groundwater models is complex and there are a lot of difficulties. For example, there is a lack of observations which difficult the calibration of these models. There is not enough data to define correctly the geometry of these models. We only have information about the surface distribution of the materials. We don't know anything about the thickness. There is also a lack of data concerning the hydrogeological parameters. Therefore, we cannot set up the parameters of the models. It's true that there are some databases that contains information about the transmissivity, but these databases are based on surface materials. Therefore, we cannot use these values. And we also have problems with the codes that we use because commonly the classical codes are designed to develop models at a small scale. Therefore, we need to adapt these codes. And finally, there are also difficulties related with the coupling between hydrological and hydrogeological models because the boundary conditions are different, but also the spatial and temporal resolution. In principle, surface water surface processes are fast, while groundwater is slow. So our objective has been to develop a methodology to construct realistic groundwater models at continental or global scales, and we have applied this methodology to construct the model of the Danube Basin. So here you can see the software code that we have used. We have used the code OpenGeoSys to develop the groundwater model. This is a code developed by the UFZ, and it solves thermo-hydromechanical chemical processes in porous media. We only solve the flow. And the hydrological model for the Danube Basin is solved using PROMET. And both models PROMET and open geodesics are coupled using the software Discharge that basically transforms the output from PROMET into inputs from open geodesics. And finally, we calibrate or validate the model depending on the available observation points using PEST or a kind of methodology that is based on ParaView. So concerning the characteristics of the model that we have developed for the Danube Basin, the model is 2D, and the third dimension, that is the thickness, is implemented through the transmissivity. So in this way, we can simplify the model, we reduce the computation time, but we obtain the same results, at least in terms of flow. So this model has more than 6 million of elements, and the size of the elements is 500 meters, and they are regular, which means that the shape and the size of the element don't vary across the model. So with respect to the temporal resolution, we perform steady-state simulations and also transient state simulations. The transient ones cover from 2015 until 2018 with monthly time steps. And finally, we use two types of boundary conditions. We prescribe the head to simulate the surface water bodies, to simulate the lakes, rivers, or springs, and we prescribe the flow to simulate the groundwater recharge. We prescribe the flow at the top of the model. The groundwater recharge that is obtained from PROMET and implemented using the software Discharge. And here in the figure, you can see, as an example, the groundwater recharge that we use for the steady-state model. And finally, we have to parameterize the model. That is a more complex step, but we have defined a new methodology to derive the values of transmissivity. So despite there are some databases that contain information about the transmissivity, as I said before, these are based on surface material. Therefore, we cannot use these databases in our models. So we propose a new approach that consists in obtaining the transmissivity from real observations at gauge stations. We obtain the transmissivity applying spectral analysis to the river base flow. So first, we choose gauge stations only with enough data to ensure a correct result. For this case, we select gauge stations with data from more than 20 years. And at the end, in the whole Danube, we use about 70 gauge stations. So, and after we compute the base flow from the river discharge by applying a filter, as you can see here on the left. There is an example. In orange, you can see the river discharge, and in blue, here at the bottom, is the base flow. And then we compute the power spectrum of this calculated base flow, as you can see here on the right. In this plot, you can see an example of the spectral analysis of the base flow, and there is an area at the beginning where the value is more or less constant. This occurs at lower frequencies, but after certain frequencies, the value starts to decrease. So the time at which the value starts to decrease is the characteristic time, and this time, as you can see in this equation, depends on the transmissivity, that is the T, the storage coefficient, that is the S, and a characteristic distance, that in this case is the distance between the river and the water seal. So, using the time that we obtain from the spectral analysis, a distance of time obtained using the topography and porosities from databases, we can compute the distribution of transmissivities. And here on the left, you can see the distribution of transmissivities for the Danube. This is the transmissivities that we have used for our model. And finally, we have to validate the model, and the validation is done by comparing the compute piezometric heads with observations. So here on the left, there is the results of the validation of the steady-state model, and you can see in the plot the fitting between compute and observed piezometric heads at the observation points. So here there are not a lot of observation points because we only have data from the upper Danube, but the results so we can reproduce at least the groundwater distribution. And on the right, you can see some results concerning the validation of the transient model. So you can see the fitting at 6 piezometers, and we observe that at least we can reproduce the groundwater oscillations. So globally, these validations of the steady-state and transient models indicate us that our model is acceptable and allows reproducing the groundwater behavior. And once we have validated the model, we can use it for predicting the groundwater behavior under different scenarios. For example, under different abstraction scenarios related with irrigation or under different groundwater recharge scenarios. So in this case, we use the model to predict the groundwater response to an irrigation scenario in some small basins located at the lower Danube, as you can see in this figure. So the irrigation scenario were simulated with ProMed, and the results of this model indicated us how much water was required for irrigation. And we assumed that this water was obtained from groundwater, and we implemented this new water abstraction for irrigation for the irrigation scenario in the groundwater model. And the results show us the response of the aquifer to this new irrigation scenario. And as you can see here in the figure, the drawdown expected with this irrigation scenario was about 5 meters. So to conclude, in general terms, we have established a new method to infer regional groundwater parameters that, contrary to previous models, is based on real observations. So our models are more realistic. And in addition, we have coupled groundwater and hydrological models, which allows improving the quality of the predictions concerning the evolution of the water resources. And as a result of this global approach, we can construct realistic groundwater models that allow us reproducing the groundwater dynamics. In the case of the Danube Basin, the model allows us reproducing the groundwater distribution and also the groundwater oscillations. And finally, these kind of models are useful to predict the groundwater response to different scenarios, and also to design water management strategies at regional scales. For example, in this case, in the Danube Basin, we have used it to respond to new irrigation scenarios. And thank you for your attention.
Okay, thank you to Elisabeth and Stanis for their presentation. Are there any questions in the meantime? So I have a look, because then if you have any questions, you can put up your hand, raise up your hand, or just ask for getting the microphone switched on. So I have a look here on the list. Yeah, I can hear a signal, but I don't see any. One. I will check again. Okay, good.
Just one note from my side. We need
Yeah.
to switch in the question answer mode. So we are still in the presentation mode.
Okay.
So no one of the participants can unmute.
Yes. Okay. And can you do this?
Yes. I will.
Okay, please. Okay, but okay, then I will have a, yeah. Okay.
So everyone should be able to unmute themselves.
Yeah. Okay. Are there any questions to the presentations from Elisabeth and Stanis? I don't think so. So then I would suggest to continue with the next presentation, which is again Elisabeth Probst from the LMU Munich, and she will present about yields and water use efficiency in Romania. So please.
Yeah, thank you. Now, yes, welcome to let's say the next thematic block. We are switching now from hydrological modeling over to crop modeling, where we incorporate also satellite data in order to determine agricultural yields and water use efficiencies. And we like to exemplify this in a test region in Romania. So, for a start, a few words maybe on the embedding of our work in Romania in the scope of ViWa. One of the goals of ViWa is the development of a global high-resolution monitoring system for observing agricultural management and for assessing the sustainability of agricultural water use. So important factors here are yield and water use efficiency. Water use efficiency is defined as the ratio between crop yield and evapotranspiration water of the crop during the vegetation period. So generally, agricultural yield and water use efficiency is the product of natural boundary conditions, which are climate, or for example, topography and also soil, as well as the farmer's management. So on the one hand, natural boundary conditions can be determined by models, and on the other hand, agricultural management can be observed by satellite data. At the very core of ViWa now is an approach to couple bromate crop simulations with Sentinel-2 Earth observation data, through which we derive actual management, yield and water use efficiency. And for this global monitoring system in Romania, in ViWa, Romania, respectively, the Romanian plain serves as a test region. So the Romanian plain is located in the south of Romania, as you can see from the map here below. It is an extensively used and fertile cropland with large agricultural potentials, but it also faces recurrent droughts. So this region features low crop yields and water use efficiencies due to poor fertilization, a low degree of mechanization, and also due to inefficient irrigation. So improving water use efficiency is key for sustainable agricultural management. The major question here is how can we derive actual yield and water use efficiency through the coupling of bromate crop simulations with Sentinel-2 Earth observation data. And here we share the example of winter wheat in 2018 with you. So our modeling framework is outlined here. We heard also before that bromate is an agro-ecological model which performs biophysically based crop growth modeling. And also in this modeling framework, bromate is driven by Error 5 data and basically the same gridded input data and parameterizations as already shown for the Danube are used. Here, detailed agricultural management parameters are required for the crop modeling, which are unknown beforehand and which we have to find out. And I will give more details on this in the next slides. So the outputs of the simulations are actual winter wheat yield and water use efficiency for 2018. And we also validated simulated yield by yield statistics on county level. Now to have a link to reality, bromate also allows the assimilation of Earth observation LAI data, which means that the modeled LAI is updated by external data streams. And in this case, we used LAI courses from Sentinel-2 images. So deriving these LAI courses from Sentinel images, this is work done by our project partners ViWa. And you will hear a much more detailed presentation on this in the following, on the workflows. In this respect, so I will tackle this very short. So there are 21 tiles covering the Romanian plain, and all of them were processed for the full growing season of winter wheat in 2018. The Sentinel processing chain for this includes some pre-processing steps, for example, atmospheric correction, crop type classification. The crop type classification identifies pixels on which winter wheat was grown in 2018, and then by help of the radiative transform model SLC, which stands for leaf soil canopy, the green LAI is retrieved for the pixels. And then a sample is drawn from the pixels, and finally a temporal interpolation is done for the sample to get continuous LAI courses for each winter wheat pixel. And finally, the output is a sample of over 10,000 pixels identified as winter wheat in 2018, for which LAI courses are available. So with this, now we go for the modeling. The first step here is to inform bromate with Sentinel-2 to find out the actual management of winter wheat. And to achieve this, we run an ensemble of bromate simulations with a large variation in management. This ensemble comprises different seeding dates from early to late, different fertilization levels from poor to high, and also different cultivar selections from early ripening to late ripening varieties. And this amounts to a bromate ensemble with over 2,000 members in this case. So now the plot shows our procedure as an example at 1 pixel. We have the Sentinel LAI course in blue and many different LAI courses coming from the bromate ensemble, which are here the red dotted lines. And we compare Sentinel LAI to the different PROMID LAIs and select the best fitting ensemble member on every pixel, which is the red solid line, for which the PROMID LAI and the Sentinel LAI shows the lowest RMSE in comparison. So the best fitting ensemble member now has a unique set of management parameters, which we identify as actual management for this pixel. So now let's have a look on the spatial results of actual management. We see the distribution of seeding dates on the left map, and apparently there's quite a variety. For example, the right seeding dates in the eastern part are very late in the year, and on the right map we see the patterns of fertilization levels, which likewise shows large differences, and most notably a clear hotspot of poor nutrition status in the center part. So let's get a step back to the methods now. The second step is simulating Sentinel LAI in PROMID to find out the actual yield and water use efficiency. And here, just for a reminder, now the actual management is known on each pixel. So we perform a direct assimilation of measured Sentinel LAI courses in PROMID simulations, which are driven with the best fitting and thus are equivalent to the actual management per pixel. And we see from the green curve, which is now overlapping the blue curve, the Sentinel curve, we see that PROMID is updated by the Sentinel LAI and exactly matches the Sentinel curve. So the assimilation gives us actual yield and water use efficiency for every pixel. And this is much more accurate with assimilation than without, because the model LAI exactly matches the Sentinel curve. So this is why we include this step, this extra step here. So now let's have a look on the resulting maps of actual yield, the map in the middle, and water use efficiency, the map on the right. Winter wheat yield amounts to 5.5 tons per hectare on average, and we see clear spatial patterns between low-yielding areas in the center and also in the northeast, and high-yielding areas in the south, which can be traced back mainly to the different fertilization levels. And on the left, you see here the plot. We also validated a simulated yield with statistics on county level for from 2018. And what we see is quite a satisfying result with a slight overestimation by the model with a trend line of 1.3. But we get a quite good correlation with an R squared of 0.53. And however, yeah, we are still in the ongoing process to improve the validation through improving our algorithms on the ensemble member selection, for example. And yeah, besides, on the right hand side, water use efficiency of winter wheat amounts to 1.8 kilograms per cubic meter. And we see on average, and we see water use efficiency patterns which are in very close relation to spatial patterns of yield. Low yields are connected with low water use efficiencies, and high yields are connected with high water use efficiencies. Yeah, and this also makes perfect sense, as higher yields cause a higher water use through transpiration, but the share of unproductively evaporated water from the soil is getting less when lifting yields. So this is a strong indication that water use is rather unsustainable in these low-yielding areas. So to conclude, the coupling of data streams of high-resolution Earth observation satellites, just like Sentinel-2 in this example, with mechanistic crop models such as PROMID, results in a deeper understanding of agricultural management, of actual agriculture and its water uses. So we derived actual management through our Sentinel-PROMID comparison, and we determined actual yield, evapotranspiration, and water use efficiency through our assimilation runs. And this approach here forms the basis for our global yield and water use efficiency monitoring system also. But of course, also further research questions arise in this respect. For example, what are regional potentials to minimize yield gaps and to maximize water use efficiency? But also, how can we close yield gaps within the limits of sustainable while at the same time minimizing our ecological footprint. So this is in the context of a sustainable intensification. We can ask, for example, how much land could be given back to nature, and we can also ask how much water could be saved. So last but not least, in a practical sense, also what are the regional tailored management recommendations for a more efficient and sustainable use of scarce agricultural water resources, this also in the context of sustainable intensification. And I think this is very important in especially drought-prone areas, like it is also the Romanian plain, where a special emphasis should be put on the water use efficiency improvement rather than yield maximization. And yeah, with this, I thank you for listening again, and I'm looking forward for some questions.
Okay. Just in the meanwhile, I was talking with my colleague Tobias, and we said that we maybe hand over in the presentation and collecting the questions in the chat, so you can use the chat function, which is the whole time available. And at the end, we'll have a look on these questions coming up, because otherwise we have to switch every time from this QA to the presentation mode, which is a bit complicated. I hope this is okay for everybody. And then I would hand over to Heike Bach from Vista. She will give a presentation about remote sensing for regional and Nexus research, please.
Thank you very much, Christoph, and also Elisabeth. You already introduced the remote sensing approach very well. So what I want to do is to go a little bit deeper in the remote sensing part, but also to scale it up to the Danube region. So as background, we are using a satellite data, mainly Sentinel-2 within the ViWa project, and that means a massive amount of data that is coming in every day. So we have terabytes of data to be analyzed, and this is done normally nowadays using cloud infrastructures and systems where you can, in parallel mode, you can really process all the satellite data. There are different platforms for this, like LRZ, we can use this, but also the food security tab that is possible. But more importantly, it's not that we do massive processing of satellite data, but how are we processing them? And there's one point that we at Vista, we have developed the SLC model, radiative transfer model, that we really simulate the absorption, transmittance, and reflectance properties of the land surface, and how also the absorptions in the atmosphere and the scattering, that we can extract from the satellite signal the information on ground, that we can correct all the atmospheric effects, and that we understand how the spectral signatures of crops develop with time, and with this we can invert the signal and learn about the properties of the crops. So it's not simple indices that we calculate and say, okay, it's higher or lower, but we really want to describe the crop leaf area, angles of the leaf angle of the areas of the leaves, or the chlorophyll content, the soil moisture of the top surface soil. These are things that can be retrieved with this approach. And we also combine it with the bromide model that allows us to even have a better understanding of what happens on ground. So what is the necessary processing step that we have to conduct every time we get a new satellite image? It's one thing, the satellite images are influenced by atmosphere, so the first step is always an atmospheric correction to get rid of the haze and of cirrus clouds and thin clouds that we can correct. But there are also thick clouds like the white one here, so we have to, at least to classify them and tell, okay, under these clouds we cannot get information, and the clouds also always make shadow, and also there the quality of the signal is too poor to go do physical retrieval there. So the classification of these regions are necessary, and at the end we have a classification of the whole region where we know where is regions that we cannot classify, where do we have vegetation that we can retrieve crop parameters for, and where, for example, is water and forest. And for the regions where we have a clear view on the surface, we can do the leaf area determination in inversion, and this can be done crop type specific if you have done the crop classification before. And this is then very detailed that we, for example, we know that sugar beet looks different from wheat, and this can be considered that we have a different leaf area when we know the crop type under this pixel. And this is done automatically for all of the thousands of images. On average, we have every 3 days, we have a new satellite image all over the globe, and that is our standard processing scheme for that. Within ViWa, we have the concept that we distribute our analysis all over the globe, but not globally. I mean, these satellite images have a resolution of 10 by 10 meter, and at present we could not achieve to have to analyze 3 years of satellite data all over the globe in 10 by 10 meters. So we said we have a different approach. We have a sampling approach that we distribute our test site, that are the little red dots here, in agriculture regions that are representative for the agriculture all over the globe. So we have covered the wheat in the same amount as it is distributed over the world, and that was quite a thing to find a solution that fits in, that we have only 150 tiles of Sentinel to be analyzed, but should be representative, that we learn, as Elisabeth explained before, the management of these tiles, how much fertilizer is used, how that is their seeding, yeah, mainly fertilization level and phenological development is taken from these observations, and not, of course, which crop type is grown where. Altogether, we analyzed 36,000 satellite images, which is about 100 terabyte of data. And you can see on the right side how these satellite images look like. It's just nice to see on the one side, but you also already see here there is a lot of variation. There are the big fields, irrigated fields here in Spain. There are the more rectangular fields in the US, and the very small ones in China. So we really had to learn how the different crops and patterns, cropping patterns are in the different regions on the globe, which is quite a challenge. At the beginning, we didn't expect that to be so complicated to understand this. Next one. So when we have such a tile, the first thing is we do a crop type classification. So we look which are the most prominent crop types in our tile. A tile is 100 by 100 kilometer, and then we selected on these fields. We selected points here. These are the yellow ones. It's winter wheat or spring wheat or maize for this tile in Russia. That are the main crops there. That we have representative, again, pixels for these areas where we can do the further analysis of the development of these crops. Yeah. That is not as it should be, but okay. So then we had, for all of the tiles, we had different classification, different crop types. Here, for example, in this European case here, we found that in Europe, in this tile, we have root crops like sugar beet, maize, barley, and wheat. And for all of these pixels here, we have typical leaf area developments. You can see there is a typical crop cycle, phenological development, where you see that, for example, winter wheat starts here earlier than the spring wheat. But you also see within this collective, we have very different maxima of the leaf area, which is mostly belonging whether it's irrigated or not, and whether it's how much it is fertilized. These typical behaviors we developed for all the different regions on the globe. This is an example. You don't see the. Let me see whether I can put in. So now you should see. Well, let's see whether it works. That here we had, for example, also very specific crop types like groundnut, and we have to develop now also observations for rice. And you see here, for example, maize in Africa has a much lower leaf area than the one here in North America. So we really covered all of the regions, and including the Danube region, which I want to concentrate further on. And for the Danube region, we now scaled up, that we said, okay, let's not only have the tile solution for that we have only specific tile. It's a specific focus area in the ViWa project. And that's why we covered many countries along the Danube catchment and the regions of the Danube. But we did here the same as described before. We selected the specific crop type. In this case, it's maize. And then we classified the regions pixels where we are sure that their maize is grown in a certain year. And we also classified these maize fields whether they are irrigated at present or not. The dark blue ones are the irrigated maize pixels. So you can see that we have only few irrigation pixels of maize in Germany, but they increase in the, for example, here in Romania, we have much more irrigation there. For these pixels, we calculated then, similar as Elisabeth showed, the evapotranspiration that is used to produce this the yield that later on is shown in the next slide here. We know also simulated for a specific year how much yield each pixel is producing using the assimilation approach that Elisabeth explained very well before, so I didn't want to repeat it here. So we have evapotranspiration, we have yield that allows us to calculate the water use efficiency for all of the pixels all over the Danube region. We had before this scene for the Romanian plain, but this is now covering the large region of the Danube. And this allows us now to do analysis, for example, on country level. This is the next slide, sorry. On country level, that we move along the river Danube, the different countries there, starting from Germany, going down to Bulgaria. And you see here on the y-axis is the yield. And here we see the evapotranspiration. And you see how the water use efficiency, it's the slope of this in this plot here, how it changes over the region, that we have a saturation level, for example, in this point here. And you see again the dark blue plots points the fraction of irrigated pixels up at present. And this allows us now to really see that, for example, in Romania, we have a lot of irrigation already that increased the water use efficiency. We are higher here in this region here. But you also see you have a lot of variation in water use efficiency all over Romania and along the Danube. So we really can observe agricultural practice, yield formation, water use efficiency all over the Danube region. We scale it up to the globe using our tile-based, sample-based approach, but it's possible nowadays also to do it on a large scale with a satellite approach. Okay, thank you very much.
Okay, thank you. I was just here in this chat. There were some problems with the presentation. I was not sure, but it was only from Estanis coming. Yeah, but I think as long as there is no one other, maybe he can log out and come in and join the session again. Okay, then yeah. We already heard a lot about water balance and discharge and groundwater, but there is, of course, another topic which is important, and it's the question how much water is used for irrigation and what impact does this have on the runoff. And this is something Tobias Hank will present to us, please.
Yeah, good morning, everyone. Thanks, Christoph, and thanks, Heike, for bringing us back to the scale of the entire Danube and already highlighting the agricultural issues that are happening there. My name is Tobias Hank, and I will now present about the impacts that irrigation practices could have or have in the Danube on the river runoff. So irrigation in agricultural practice is used for many, many different purposes. For instance, for the product refinement, to create really fresh looking fruit, for instance. It is applied to facilitate harvesting. Especially for potato harvesting, water is applied to protect the sensitive skin of the potatoes from damage during the harvesting process. But of course, above all, irrigation is applied to increase yield quantity because it just takes the precipitation variable out of the equation from the environmental variables that are needed to produce yield on the land surface. And what is maybe not so much known among most people is that irrigation also is required to unlock the potential of the nutrient supply in the soil, because if there's no water available, also all the nutrients in the soil, they cannot be used by the plant. The reason why I put this slide in is because people coming from an environmental perspective often maybe associate irrigation with a negative thing. And I wanted to highlight that irrigation indeed can be a very, very positive thing. So it makes quite a lot of sense to think about how irrigation could be implemented in a sustainable way. And this is something that we're doing here in the frame of the ViWa project. Wolfram already highlighted it in his presentation this morning that irrigation in the Danube currently is not a big issue. Only 1.5% of the cropland actually are irrigated, but there exist plans to largely expand irrigation measures in the Danube. And this will cause, of course, competition about the water resources between different sectors. And of course, excessive consumption of water will threaten the ecosystems. So we expect a rapid increase of irrigation measures in the Danube, mainly in Hungary and in Romania. So the trend is going up here, but from a very, very low level right at the moment. So what we did in the frame of the ViWa project is we created a tool that allows us to analyze these conflicts between water use in different sectors. And what we use is we use the PROMET model. If you're not so familiar with the PROMET model, I'd like to cordially invite you to watch the videos in our marketplace. There are some videos uploaded there which give quite detailed information on the PROMET model. I just want to highlight the irrigation option that PROMET has. So if we have a normal rain-fed agricultural situation, the natural soil water reserves are consumed for the crop growth, transpire through the canopy, and exit the canopy into the atmosphere. But if there's mild water stress occurring on one of the pixels of the PROMET simulation, then the model offers us different options to include irrigation. Most of the time we use the sprinkler irrigation option because it's the most realistic assumption. There is interception evaporation happening from the leaves, so the leaves are wetted from above. Some of the water is dripping from the leaves onto the soil, some of the water is evaporated directly from the leaves, and some of the sprinkler irrigated water enters the soil column and then can be transpired again. So different options are possible. From the perspective of the PROMET model, the land surface consists of individual pixels. These pixels are formed by a 4-layered soil column. On top of the soil column, a dynamically simulated canopy develops. And at the bottom of the soil column, there's a groundwater body. And the growth that we simulate in this model really is the result of the interaction between soil and atmosphere and the canopy itself, because we really go to the gas exchange of the system to simulate the carbon assimilation that is happening independent of the environmental variables at one point in space, at one point in time. So this is the moment where we bring the hydrological cycle and the carbon cycle together. And Elisabeth has quite impressively shown already that we managed to reach very, very high precisions in both terms, in terms of runoff modeling and in terms of yield modeling at the same time. And this is something where the ViWa approach really goes beyond the, let's say, normal hydrological modeling that we see nowadays. So let's dive into one of those pixels, very, very detailed, go into one single point at the land surface, and let's have a look at the model results at an hourly resolution. I want to highlight this graph first. This is the soil moisture in the 4 soil compartments. The blue is the most shallow one, and the yellow is the deepest and largest soil compartment. And we can see these very dynamic fluctuations of soil moisture happening independent of the weather conditions and independent of the transpiration stream that is extracted by the canopy. What we can see here is, and this is just an example for maize crops now, I'm mostly talking about maize crops in this talk actually, that there is some water stress occurring during the summer months. So the stomates in the model, they begin to close, transpiration is reduced, and if transpiration is reduced, the uptake of carbon dioxide from the atmosphere is reduced at the same time, so growth is limited. So if we let the model run here on this pixel, we receive a leaf area index curve here, and the gas exchange accumulated over the entire growing season amounts to a yield of 8.2 tons per hectare, and a water use efficiency of 2.4 kilograms per cubic meter of water. So if we now switch on the irrigation module, we can see here that PROMET, independent of the water demand that is exerted by the canopy, provides water on top of the plants. And this helps to reduce this decrease in soil moisture up to a degree where the water stress, the closing of the stomates, it's very, very much reduced. It does not completely vanish because there are some evaporative losses, but it is very, very much reduced. And this results in a higher growth, maybe you can't really see it, but this curve is a little bit broader compared to that one. This results in a higher growth and a higher yield, and also in an increase in water use efficiency. So applying irrigation increases yield, and it increases the water use efficiency. Okay, now we go back to the catchment scale again. So we zoom out again and have a look at the situation in the entire Danube. On the left-hand side, we see the simulated yield map in tons per hectare, only for the maize yield. And we can see that these are all results just for the year 2017. We have an average yield of 5.9 tons per hectare. Elisabeth has already shown us that the yield very well agrees with the Eurostat numbers. And we can see that this is regionally very, very different. We have the more higher yields here more in the upstream countries, and we have the lower yields here, mostly here in the central part of the Pannonian. All the pixels together amount to a total production of 34.4 million tons of maize being produced in the year 2017, according to the model. The assumption behind this is that all these pixels are fertilized in a very much standard way. All the crops are grown in a rain-fed mode, and we assume no pests. So perfect growth according to the natural conditions here. And we achieve a water use efficiency of 1.7 kilograms per cubic meter of water here. So if we now take this model and we assume in a scenario mode what would happen in the Danube if we would switch on the irrigation module and introduce irrigation really at the large scale and try to irrigate all the pixels in the Danube according to their actual demand, we end up with an image like this. 512 millimeters of irrigation water would have been demanded for the season of 2017 on average over the entire Danube. And again, we have a very, very heterogeneous picture in the upstream countries, and also here, less irrigation demand, and in the central region of the Danube, very, very high irrigation demand also in the year 2017. And if you remember, 2017 was pretty much an average year. The summer of 2015 and 2018, they were actually a lot drier. So we could expect, and also our research showed that for those years, even more irrigation water would be required. So the effect of this assumption of irrigation now we assume not only irrigation for the whole plain, but we also assume a full fertilization, because as I already told you at the beginning, only if I irrigate the crop, the full potential of the soil nutrients can be used. So we also upgraded the fertilization here. We can increase the yield, and it's not the actual yield anymore, it's now the potential yield, the if the fields would have been irrigated yield. It really surges up to 12.5 tons per hectare. The total production nearly doubles to 72.9 million tons in the Danube. And also the water use efficiency, it goes up, not quite so steeply as the yield, but it goes up. So the total irrigation water that would have been required to irrigate the entire Danube amounts for the year 2017 to 5 gigacubic meters, which equals a cube with an edge length of about 1.7 kilometers. For the year 2017, for a more extreme year like 2015 or 2018, we also have done simulations where the size of this cube here easily doubles or triples. So the question that now arises is, where does this cube, and if we imagine a cube of that size in relation to the size of a riverbed, the question is now, where does this water come from? And the PROMIT model here offers two options. About the first one, we already have heard something from Estanis. Of course, we could just take the water out of the groundwater from the pixel directly underneath the place in space where I'm actually modeling. But I now want to highlight the second option that the PROMIT model offers, and that is to extract the irrigation water directly from surface water. And this is done by searching for the closest point in the river network to the place where the irrigation should be applied. There are some assumptions that have to be met. For instance, the model assumes that a farmer would not be willing to invest into pumping systems that pump the water over more than 10 meters of elevation difference, not more than 10 meters uphill. And the second assumption is that a lateral distance of 25 kilometers is not surpassed by the simulated irrigation system. So these are the two major assumptions that the model has. And if we now simulate this and we apply these assumptions to the river network of the Danube, again, this is only the year 2017 show here, we can see that the results of this are very, very heterogeneous, both in space and in time. There are moments in the year, for instance, in April and in May, where there is no real effect by irrigation on the runoff in the riverbeds. The way we have to interpret this figure is all the blue colors indicate that the runoff in the river basins is nearly unchanged by the irrigation, and the more bluish, yellowish, and reddish the colors become, the more influence we have on the river flows. So early in the year, there's not much influence by irrigation, simply because the crops do not require much irrigation water during these times of the year, and the flow usually is high after the winter. But the more we progress through the summer month in June, in July, and then climaxing in August, we can see that there are some rivers where we have these really dark red colors, which means that nearly 100% of the river flow would be required to irrigate all this region of maize fields. So if we now compare this to the actual flow, if we now not directly compare, but if we analyze these findings at the direct points of the gauging stations, we again can see these gradient ranging from the west to the east of increasing influence of the irrigation on the river flows. You can see that at the upper Danube in Germany here, or on the border to Austria in Achleiten, we have nearly no impact of the irrigation measures on the stream flow. The way we have to interpret this figure is the blue line gives us the runoff at the gauging station at the assumption of rain-fed agriculture. The red line gives us the runoff at the gauging station under the assumption of irrigation water being taken out of the river. And the dashed line here gives us the difference between the two curves. So the more we go downstream here, we can see the more intense the difference between those two lines becomes. And even things are happening here which are only possible in a computer. For instance, we can see that this red line here even goes below the line of 0, so that we have a negative flow here. There's more water being taken out in the simulation of the river than actually has ever been in there during that time of the year. So we get a very, very detailed picture of the impact of irrigation measures if they are applied in the Danube on the different gauging stations, on the runoff at the different gauging stations. And this has impact on other water uses. We see here an image that shows us the 31 largest river runoff power stations in the Danube. And we can see that most of them are located in a situation where already in the slide before, we did not see much of an impact of the irrigation on the runoff. But there also are some here more downstream, for instance, here at the Iron Gate, where we can see that, yes, we have a direct impact of irrigation measures on the river stream. And those are runoff power stations that are producing a lot of electricity. If we assume the normal, natural, rain-fed agricultural conditions in the Danube, they produce about 37,500 terawatt hours of electricity. And if we switch on the irrigation option in the model, we can simulate the loss in production, the trade-off between irrigating the land surface and producing electricity from the river flow. And we can do this for every single of these power stations. And we can see again a gradient ranging from west to east with low impacts, low losses. These columns here, they just show the loss in revenue that would be observable if the entire Danube decides to irrigate all the fields in hydropower production. And this is really, now we're at the core of what we wanted to do with the ViWa project. We wanted to create a tool that allows us, through the simulation of this coupled water, food, energy nexus, to directly address these trade-offs between different uses of water and water use scenarios. And I think with the PROMET model and with all the coupling and all the cooperations done in the ViWa project, we have quite succeeded to do this. And this now enables us to tackle the uncommon research questions. We now really want to analyze how we could use this tool to build scenarios, to analyze scenarios, to really find the point of the least trade-offs between the boosting of the agricultural production, which is necessary to feed the people there, which is necessary to boost economy, and at the same time analyzing the sectorial impacts on other sectors, on industry, on hydropower production, etc., etc. And then one point finally enters the picture also, and these are the ecological impacts. I have now not analyzed the ecological impacts. I've just shown the quantitative numbers. And the ecological impacts, this is something that Anna is now going to analyze for us. Thank you very much for your attention. I'm happy to take your questions.
Okay, thank you, Tobias. Just only because, okay, this presentation ended in a fine way that Anna can directly continue, and I don't have to say any more words, but it was so smooth, so please continue, Anna.
Yeah, thanks for this nice introduction, Tobias and Christoph. My name is Anna Schlattmann, and I will now present you on behalf of the project team of the Leibniz University of Hanover, the last part of the Nexus analysis, the ecological implications on water use in the Danube Basin. As Tobias already introduced, agricultural production has to increase, and there are several ambitions of Danube Basin states to increase agricultural production by irrigation. But at the same time, the society gets more and more aware of the fact that biodiversity and other ecosystem services have not only intrinsic value, but are crucial for our well-being and of the functioning of our economies. But they also need water to be sustained and to be maintained, though these issues are up to now seldom incorporated in assessment tools. And governance would need such multi-scale assessment tools that can address water use conflicts in order to support or to achieve sustainable water use, and to steer water management from local to global back to local levels. So the main objective of our project team was to develop such an assessment tool that addresses these issues in order to complete the picture of water use implications within a river basin. Our methodology should basically improve existing assessment methodologies by building on legal standards and transparently communicating them in order to show what are minimum objectives or minimum standards that should be met to meet legal obligations. The method should particularly consider the spatial relationship between vulnerable wetlands or ecosystems and agriculture and its water use. And third, it should be a multi-scale approach to address different water users and different applicants and to support governance from local to global back to local. Therefore, we conducted our assessment approach in 4 consecutive steps. At first, we did a broad literature review about legitimized standards for sustainable water use, which are the background or the yardstick of our assessment. Then we operationalized these standards and implemented them in 2 different assessment parts. One on sub-basin level, the ecological sustainability assessment, and on grid cell level or local level, a risk assessment. With the data generated by the PROMET model and from UFZ Leipzig for groundwater, we carried out a status quo assessment in the Danube River Basin. And finally, we also conducted a scenario analysis for the case of maize irrigation, what this would mean for the ecological sustainability of water use in the Danube Basin. The complete or entire assessment tool is composed of 2 main parts. It is the ecological sustainability assessment on sub-basin level with the criterion of the Water Sustainability Index. And the second assessment part is the ecological risk assessment that is composed of 3 sub-criteria: a water depletion index, the compliance with environmental flow requirements, and a risk for groundwater dependent ecosystems. Now I will explain the concept of the different indicators and criteria and the main results for the first application in the Danube Basin. The Water Sustainability Index on sub-basin level is a supply-demand ratio, where supply are the monthly renewable water resources that are generated by precipitation and discharge from upstream sub-basins. And this water supply has to serve first so-called priority water users, which we identified as domestic water consumption and the water consumption that is needed to sustain ecosystems and their services, which is implemented through the minimum river flows and evapotranspiration of natural and near-natural ecosystems. And the remaining water is available for further water uses. In our case, we implemented agricultural and industrial water use. And when this is not higher than the remaining water sources, we call a sub-basin with sustainable water use. Otherwise, water use is unsustainable. Here you see the results for the Danube Basin in the average year 2017. So it's the same year as Tobias Hank already presented the maize irrigation scenario for river discharge, so we can compare a little bit. And in the month April and September, relatively high amount of sub-basins has sustainable water use or stays within the sustainable limits, though the summer months, June to August, have a relatively high share of basins with unsustainable water use, which goes up to almost 80% in June and July. The second assessment part is the local analysis of different risk criteria. There we have the water depletion index. This estimates the degree to which crop growth already exploits the monthly renewable water on grid cell level. Then the effects on environmental flow, so whether the river discharge in the streams is sustainable or already lowered to a degree which is unsustainable. And the last criterion is the risk for groundwater dependent ecosystems, which is estimated as risk that water pumping for agricultural irrigation, for example, or on agricultural areas negatively impacts on vulnerable groundwater dependent ecosystems. Now you see the results for the application in the Danube Basin for the water depletion index, where we already see that the normal crop water use, normal crop water depletion is very high during the summer months, June and July, and that this has also impacts, negative impacts for the environmental flow requirements or the compliance. The graphics are not that good, but I hope you can see the different colors. So in dark green and light green, there are sustainable river flows, and from yellow, orange and red, we have unsustainable river flows. On the left side of the chart, you see the development from May to September for the larger streams. But due to the use of the high-resolution model data from PROMET, we could also model the compliance with environmental flow requirements on 1 kilometer resolution, which you see on the right side. So when we have the entire picture of the Danube, it seems that there are large regions which are sustainable, and in fact they are all about 60%, even in the summer months, which have sustainable water flow or river flow, and only 40% with unsustainable. But on the detailed picture, we see that there are several hot spots with really very unsustainable river flow, already without irrigation scenario. Oops. So, and the last indicator, the risk for groundwater dependent ecosystem, also shows that 2/3 of the area, which is of the agricultural area, would have negative impacts when we introduce their irrigation from groundwater, because the groundwater table would drop down and disconnect the groundwater dependent wetlands and ecosystems from their additional water sources. So this is the status quo without irrigation, and we see that there we have already some regions where there's a high competition between different water users and water uses. But if we introduce now the irrigation scenario, as Tobias Hank already presented, there are significant changes in river flow, and particularly for the months July and August, we have severe impacts on the compliance with environmental flow requirements. We have an increase of up to 7% of unsustainable river sections, or river sections with unsustainable flow. But in the chart on the right side for August, we see that it's not only the 7% increase, but also the share of classes with very, very unsustainable use in the diagram colored in red and purple and also orange increases significantly. And those colored in red and purple are ecosystems which would be affected or impaired so much that we almost destroy completely the aquatic ecosystem. But we have not only negative impacts on the aquatic ecosystem themselves, but also on wetlands which are in close distance or very close to the major streams. And we mapped that 2% of the Danube Basin is covered with wetlands or open water bodies, and that already in status quo, 15% of these wetlands are at risk to be negatively impacted from low river discharge, so that they cannot get enough water from flooding, etc. And that this share would increase about 11% to 26%, so 1/4 of all wetlands in the Danube, which would be affected when we introduce this large-scale maize irrigation. So concludingly, we can say that already now almost 80% of the sub-basins face unsustainable water use during some summer months, and that river flow is would increase, or its unsustainability would increase significantly with effect on wetlands, particularly in the center and in the lower Danube Basin, which is from ecological view not on track to meet the water-related SDGs 6 and 15, particularly because in the lower Danube and in the Delta region we have the UNESCO World Heritage Sites and which have high value and should be protected. Concludingly, we can say that the multi-scale ecological sustainability assessment, which is based on this legitimized criteria, can be used for strategic basin water management because it incorporates the local scale and the regional scale and the whole basin and is able to switch between the different levels of governance in order to achieve sustainable water management. This is everything from the ecological sustainability assessment, and I thank you for your attention. And now I directly hand over to Elisabeth for the synthesis of all our Nexus analysis in the Danube Basin.
Yeah, thank you, Anna. So we are now at the point where we can condense our results in a synthesis, including all elements of the water food energy ecosystem nexus, because we have tackled all elements now. So as you have heard, we carried out an integrated assessment for the year 2017, in which we studied the impacts of large-scale maize irrigation on this nexus, just as a close-up. And we learned now that in terms of water, the irrigation water withdrawal for agriculture amounts to about 5 billion cubic meters. And the water is mostly extracted in Hungary, Serbia, and Romania. From this, the nexus element food is very much benefiting. So the maize production roughly doubled from 34 to 73 million tons in the whole basin. And assuming a market price of 160 euros per tons for maize, this is equivalent to an increase in volume of sales of about 6 billion euros. The irrigation water abstraction from the rivers lead to a downside concerning energy. So hydropower production is reduced now from 37.5 petawatt hours to 36.7 petawatt hours, and at an electricity cost of 4 cents per kilowatt hour, this is equivalent to a reduction in volume of sales of about 30 million euros. So thereof, the highest losses of volume of sales occur at Iron Gate 1 and 2, each with about 10 million euros, as you have seen on the slide in Tobi's presentation. And this loss is mainly caused by Hungary through its very intensive irrigation in the Pannonian Basin. And from this, the most affected countries are Serbia and Romania, as on the one hand, much irrigation water is extracted upstream and is no longer available for irrigation downstream. And also on the other hand, the highest financial losses are suffered by Iron Gate 1 and 2, which are on Serbian and Romanian territory. But however, when you look at the numbers, the losses for energy production are only a fraction compared to the benefits in agriculture. And yeah, much more severe are the ecological consequences arising from this, as Anna has impressively shown you. So maybe you are the expert, Anna, so maybe add your point on the ecosystem synthesis.
Yes, so as Elisabeth already said, besides the negative impacts on energy production, the benefits for food production get also on the costs of the ecosystems and the nature in the Danube Basin, because the aquatic ecosystems and also their related functions get lost or decrease. So related functions are, for example, water purification, flood protection, recreation, or climate regulation. So it is hard to monitorize these functions as, for example, the loss in energy production and the reduction of volume of sales, but it's clear that there will also be economic and social disadvantages which are coherent to this loss of ecosystems. And as I already mentioned, the decrease of sustainable river sections varies between 3 and 7% during the vegetation period if irrigation is introduced, and this would lead to also to an increase of threatened wetlands of about 11%, particularly in the lower Danube and the center region. So this is the end of our presentation part, where we end with the synthesis of our Nexus analysis. And yes, now you're invited to discuss with us about this example.
Thank you, Anna. So we switched over to the Q&A session mode, which means that anyone who has a question could switch on the phone, the microphone, and start. And during the presentation itself, there were no questions, so we could start with now with any question from the audience. So are there any questions? So please feel free to start.
One note from my side, Christina von Haaren sent the voice recording message. I think maybe she clicked on the wrong button, but
okay.
maybe we should, I don't know how this works, but maybe we should just start her voice recording message. I will try this out.
Okay.
Okay, so it's nothing on it.
Okay,
then maybe I will just unmute her because I can do this as a host, and I think I will have a look where she is.
So at the participant, I think the first in the row. Ja, genau.
Hören Sie mich?
Yeah, now we can hear you. Good. Sorry for this.
This is a little bit puzzling.
Yeah.
Thank you very much for the excellent presentation of all the participants, and I'm proud of the team. I just wanted to add a last remark about the water, energy, food nexus, biodiversity nexus, because the monetization of the ecosystem services, or especially of the biodiversity services, if you would call it like that, is so hard and very uncertain often. We really went back to the legal basis of the evaluation, and that means because the biodiversity is not represented on markets, we cannot really put a price on it. But the legislator also saw this problem, and we have a lot of international and national acts who protect biodiversity. So what Anna showed, the 3 to 7% loss of biodiversity is protected biodiversity, and so it would be a breach of European and international law to impair these or destroy these ecosystems. that's just a point I would like to add. So there is an interplay between economic and legal arguments here in this nexus. Thank you.
Okay, thank you. Are there any more questions or comments you would like to add? So I'm not 100% sure if how it works technically. If someone wants to say something, I think if you ask for getting the microphone switched on, we can see this and then we can turn it on. So
the trick is not go into the chat, but go to the audio video function.
Definitely.
Yes. So everyone will see like a microphone and the camera like sign on the above, just on the video where all the pictures are. So just there you can mute your microphone or unmute your microphone.
So maybe I take the chance to unmute my microphone. This is Wolfram. I mean, Christina, what you just said is very important, I think, and we have these 4 points here: water, food, energy, ecosystems listed in the synthesis, and this synthesis in a way may leave us a little bit lost, because we have put these different pillars of this whole analysis, nexus analysis, on a slide, and then the big question is what's next. And this is where I think the discussion between science and decision makers and society has to start. We are not in a position to make a decision what is right and what is wrong here. And I think from my practical understanding of how life is working, there is of course a legal framework that we are living in, and that is restricting us in terms of ecosystems to certain limits of interference, as you said, Christina. But on the other hand, there is, of course, powerful influencing groups that want to take these 6 billion euros per year that can be made as a volume of sales in this whole watershed. So this is not answering the question of how to turn these things that we have found out into reasonable political action. This has to be done by society, and we have the purpose to, as scientists, to provide this information and provide information on the dimensions. This is my standpoint to it. But I would like to have more contributions to this discussion.
Yeah, let me just add something. Now when we put the tools together and use them as a system, this system, and provide this to practical, maybe water administration decisions on the basis of what we have achieved together, you can really help administrative managers to define the quantity farmers can take for irrigation in single cases. And I think this possibility to downscale what we have said and show them the legal limits of what they can allow, for instance. So it's a little more, I would say, than you just outlined, Wolfram. But of course, the political decisions are made on EU level and national level, as we just found out. This is we can't rely on sustainable decisions there, but nevertheless, on local scale, it is possible to work against the global or the European trend at present to let agriculture run wild.
Yeah, thank you, Christina, and maybe one other thing that I would like to point out this instrument that we have developed here is only one example, but I think the major power of this instrument can be released by now looking into in more detail in the question of, could we possibly reduce the ecosystem impacts to almost zero and still have, let's say, a reasonable size of increase of agricultural production through irrigation? As Toby pointed out, irrigation per se is not something that is bad or something that should be avoided, but have systems developed that are of very low impact in terms of ecosystems, but still give you the food production that is needed. I'm thinking about, and it has been mentioned, the sustainable intensification issues, where we could think of maybe increasing production on a smaller piece of land and giving back land to nature, and still have the same food production and have the food production that we need, but on the other hand have intensified production, sustainably intensified production on the one side, and on the other side giving back land to nature. And my big question then would be, where is the priority land that should be given back to nature? Not give back to nature some land that nature doesn't need. Let's put it this way. But give land back to nature that is the most valuable land. And which would be the most valuable land that is taken from agriculture and given back to nature in the Danube Basin? This is something that I'm very curious about, to look into these different scenarios, the water, food, energy, ecosystem scenarios, and analyze these scenarios and come up with proposals to politicians and decision makers that go beyond what we say today, just the simple numbers. But we're very close to that, I think, and the tool can be used for that. Thank you. So Anna, Christina, what do you think? Where would be the most valuable land in the Danube Basin?
Anna knows better, but we already now can quantify the water available, surplus water available for agriculture in a sub-basin. Then it's a question of distribution. Of course, you can use technical means to better distribute the water than right now. And we can downscale to the, you could say, to the plot or to the agricultural enterprise, and say, when you want to extract water in this place, then you would endanger ecosystems or not. So I think we can do what you are looking for, Wolfram, with this kind of combined instrument we have now. So it's Anna will say how we will become better on local scale. Anna, maybe you can add that when we have certain data, yes, which we didn't have on the.
Yes. So for Wolfram's question, where would be valuable land, or where is probably the most valuable land that should be protected from ecological perspective? I think this is really from this first analysis we did in this conflict area in the center Danube and the lower Danube. So what Elisabeth and Tobias already pointed out, where the Discharge is, I think there is the highest need of irrigation to increase food production, but there are also the largest impacts on the environment or on the stream flows. And as I already mentioned, in the Danube Delta, because there the river discharge is not that much unsustainable, but it's a very, very highly protected wetland. It's a Ramsar site. It's, I think, one of the biggest Ramsar sites worldwide, and the river, the biggest, largest river delta worldwide. And since beginning of the 1990s, UNESCO World Heritage Site. And so in wetlands, it's not the case that there's the need of a very, very high negative impact, or this impact needs to be all over the year to damage the wetlands, but only damage throughout some summer months can have detrimental impacts for years or decades, or even destroy the wetland for the entire time. And what Christina mentioned, how we can improve our analysis in terms of ecosystem damage and impacts is, for now, we can, for example, the risk for groundwater dependent ecosystems, we cannot quantify this yet, because therefore our data resources are too weak, because we could improve this assessment if we have more detailed information about sectoral water use, disaggregated data for location of, for example, industrial water use, and also which sources of water are used, because for now the general available data on, for example, industrial water use is not disaggregated. We have only national values and only the amount, and not from which source it is taken, whether it's surface water or groundwater. And this makes it very, very difficult to estimate concrete impacts on valuable ecosystems, because we don't know exactly where water is taken and which water is taken. So we can only denote a risk if water is taken, would be taken from this source at this point. So if we combine our methodology with more localized data, we could also improve reliability of the results.
Okay. Now we are approaching 12 o'clock. Are there any very pressing questions left?
Yes, there is a question, I think, from Asia, so I think we should not skip it.
Oh, of course not.
In the chat.
In the chat. There we go.
I don't know how to pronounce the name. Sorry.
Ingoyet, interesting research. He says, interesting research and excellent presentation. My question is your research modelings are mainly based on satellite data in case of transferring, adapting this concept to other regions, Southeast Asia, where technology equipment are less advanced. Do you have any recommendations for alternative research methods for the modeling instead of satellite data? Well, I can try to give you an answer to this, or try to find an answer to this. This satellite data is available around the globe. I think satellite data is a very good source. I think there are ways for countries that are in a developing phase to tap these resources. For example, on the food security thematic exploitation platform, which is financed by ESA, and which is giving you access to this kind of data, also give you access to computing resources where you can play with this data, extract the information from this data, and so you are able to explore what this data can mean for you. Of course, this is a long process of bringing this data to all the users around the globe, and I think this will advance in the future. But I think if you want to go into a deep analysis and of the complex relationships, you have to rely on data on the ground, and usually the problem is that this data is not existing. So I'm afraid that I cannot show you any simple alternative to satellite data for a large part of the globe, because the data is just simply not existing. We're having another part of the project that we have not shown to you, and this is the Zambezi in Africa, where we have similar problems as you pointed out, and where we are finding out that satellite data can be very useful for that. So I can only encourage you to maybe also try to use it and go into this field. The data is for free. There is no charge on the data. And the computing resources can be found in different places around the globe. So I hope that gave you a little bit of inspiration for your own work in Southeast Asia. And maybe we can stay in contact on this for the future. Now that we have a little bit after 12 o'clock.
Wolfgang, just wait. I saw that he was just tipping in something. I don't know. Maybe.
Thank you, Professor Marza. Was a message.
Okay. Okay.
Okay.
Thanks.
Thank you for your contribution. I want to thank the whole ViWa team. First of all, for this excellent collaboration. You may have experienced the collaborative spirit and the transdisciplinary, interdisciplinary spirit that was developed within this project by this presentation, how all the different parts were working together. You also experienced that we have a lot of future research questions that are driving us for future research work in this field. I think our experience is that this can be relevant to society, and this is important for all of us as scientists, but also for society. And we should play our important share in solving the future problems that can easily be denominated, but cannot easily be solved. And this is what we found here also, specifically with the ecological, the interference of humans into the natural system and the ecological footprint that we are leaving behind, which is too large. I want to thank Adelphi, and I want to thank Mrs. Conrad for giving us the platform here and providing all the resources for doing this side event, for recording this side event, for making it available until the end of the days. Everybody can look at it even in 2,000 years, I hope, and see what we have been doing here today. Thank you very much. We're now going, it's Friday here, we're going into the weekend, and I wish to all of you a nice weekend and a relaxing weekend after this week of Grow and ViWa and discussions and everything. Thank you very much.
Yeah, also from my side, thank you for those very interesting insights into the ViWa project and the results. And the recording of this event will be available at the ViWa booth on the virtual marketplace for the next 4 weeks, I think. And yes, with these words, I would also like to close this session and thank you for your participation. And yeah, have all a nice weekend. Bye.
Goodbye.